Okay, so we've looked at a lot of things in this unit so far, starting with the dilutions, which, as we mentioned a few times, really kind of the meat and potatoes of a lot of what we do in dosage calculations. And we had, of course, the basics of dilution, and we might have something like this. In a 2:9 dilution, what is the ratio of serum to saline? So 2:9 dilution is 2/9. But in a dilution, what does the top number represent? That is the parts of, there it is, serum. And the bottom number represents parts of total solution. And that's not what we're looking for here. We want that ratio of serum to saline. So to create that ratio, serum is still going to be on top. We want the parts of saline on bottom, of NS. We had 2 parts serum over here, so we still have 2 parts of serum. How many parts of saline do we have? Yes, out of 9 parts of total, if 2 of those are serum, 9 minus 2 gives us 7 parts that are saline. So the ratio of serum to saline is 2:7. And we could use those dilutions for mixing different solutions. We might ask, how much 1:8 dilution? Now remember, when it asks how much 1:8 dilution, that's asking, when it asks how much of this dilution, how much total solution can be created. So we're asking for the total solution. How much 1:8 dilution can be created with 30 milliliters of serum? So our serum to total solution is what our dilution represents. So the 1:8 does represent what we have and what we're looking for here. We have 30 milliliters of serum, and we want to know how much total solution that'll create. So simple cross multiply and divide. 8 times 30 is 240, divided by 1 is still 240 milliliters. So we can create 240 milliliters of that 1:8 dilution, total solution. Now the other big process we have with our dilution is testing. If we exceed the limits of a meter, so most of our meters have a limit of 800 milligrams per deciliter, whether it's a urine or a blood test. Let's say that after we've exceeded the limits of the meter, we take a sample. We're going to mix 40 milliliters of blood with 120 milliliters of sterile water, of saline. The diluted reading is 218 milligrams per deciliter. Find the true reading. So there are two steps, two things we have to find here, one intermediate step. Can anybody tell me what the first step is that we have to find? The first thing we have to find. We have to find the dilution of the blood in saline. Remember, the dilution is going to be the serum, in this case, that's the blood, to total solution. We have 40 milliliters of blood, of serum. What is our total solution down here? Is it just 120 milliliters of saline? I see some of you shaking your heads. No, it is not. It's not 120 milliliters, it's 120 plus the 40 milliliters of blood. It is the total amount that has to go in there. So that's going to be 40 milliliters over 160 milliliters. The milliliters will cancel out. 40 over 160 will reduce to a 1 in 4 dilution. So that's the dilution that was performed on this blood when we added the saline to it. Step 2 then is to calculate the true reading. In other words, the undiluted level in the blood, or the actual level in the blood. So we have a 1 in 4 dilution. The reading, the meter reading, was 218 milligrams per deciliter. We know, of course, that that is smaller. It's diluted, so it's smaller than the actual reading. So we put the 218 on top with the smaller number, the 1. And we will cross multiply and divide. 4 times 218 divided by 1 gives us 872 milligrams per deciliter. Now, I didn't specify what we were testing, but if we were testing like blood sugar or something like that, that is obviously getting up into a dangerous level. We use these dilutions to dilute not just pure substances, serums, but we went to diluting existing solutions that already had percentages or concentrations in them. For example, find the new concentration after a 36% solution is diluted to 9. So in other words, that 36% solution is taken through a 2 in 9 dilution. So we have a 2 in 9 dilution. Now remember, the 36% is going to be the higher percentage. So the old concentration always goes on bottom with the bigger number, 36%. And we'll cross multiply and divide to find our new concentration. The other option is just to take 36% times 2 9. It's going to do the same thing. It's still 36 times 2 and then divided by 9. So 36 times 2 is 72, divided by 9 is going to give us 8%. So that new concentration is at 8%. We use this form of the dilution to come up with our change of concentration formula. C1V1 equals C2V2, which allowed us to ask such questions is, find the new concentration after 120 milliliters of saline, of sterile water, is combined with 30 milliliters of 45% solution. So again, C1, V1. We're going to start with the one that we have both for. We started with concentration of 45%. And again, we can make that 0.45, or we can just leave it as 45, as long as we do the same with all of our concentrations in this problem, times the volume V1 of 30 milliliters. And that has to equal C2, but we're trying to find that new concentration. So C2 is what we're looking for here, times the new volume, and this is where we have to be careful. We added 120 milliliters to it, but we had 30 milliliters already there. So I'm going to do the 45 times 30 here, which is 1,350 equals C2 times combining the 120 and 130 is 150. So to solve that, it's just solving an equation. C2 is multiplied by 150, so we are going to divide by 150, which is going to give us 9, I believe. Yes. So 9 equals C2. So it says the new concentration is 9%. Which brings us up to where we left off right before spring break, actually doing some of the dosage calculations. The simple dosage calculations were where we had a doctor's order of 800 milligrams every 6 hours. We looked at our label, and let's say this is to be administered peel by mouth, orally. So in our label says that this is concentrated at 250 milligrams in 4 milliliters. So to find the amount to administer here, we always start with the doctor's orders. And we try to translate that using our dimensional analysis or our unit conversions into what is actually going to be administered to the patient. So our doctor's orders, 800 milligrams. Now, since this is given orally, that means we're not setting up an IV or anything like that. We're actually giving the medication to the patient. So the 6 hours here simply means that's how often we're going to do it. So in this case, the 6 hours isn't going to affect our calculation. That just means you have to put on your schedule every 6 hours you're going to go in and give the patient that medication. So 800 milligrams is the doctor's order. We put that over 1. We're trying to figure out how much to administer for each administration or every 6 hours. And now we want to get rid of the milligrams. We have this equivalency right here with 250 milligrams. That had to go on bottom, so it'll cancel out. And that 250 milligrams is equivalent to, or is carried in, 4 milliliters. So the milligrams cancel out. Now we have 800 times 4 milliliters, which is 3,200 milliliters, over 1 times 250. To get the number of milliliters to administer here, we have to divide that out. 3,200 divided by 250, which is going to give us 12.8 milliliters. So every 6 hours, we will have to go to that patient and administer 12.8 milliliters of that medication. So from there, we went on to IVs. And IVs can be given, flow rates can be given in a lot of different ways. So let's say we have a doctor's order to administer 2,000 milligrams of medication over 4 hours by IV. Our label states that this medication is concentrated at 500 milligrams in 40 milliliters. We want to find here our flow rate in milliliters per hour. And that's always very important to look to see what we're trying to find as our units in our solution, because these IV flow rates can be given milliliters per hour, they can be given as milliliters per minute, or as we've seen, they can be given as drops per minute. So this one is milliliters per hour. So once again, we'll start with the doctor's orders. 2,000 milligrams over 4 hours. Now, there are some people that like to divide these out as we go, and you can do that if you wanted to. You could divide by 4 here to get 500 milligrams over 1 hour, and that would be just fine. But rather than doing a whole bunch of calculations, I usually just string them all together and go from there. Now, we look at what we have here. We have milligrams on top and hours on bottom. In our answer, if we look at the units, we want milliliters on top. So we know the milligrams has to change. We want hours on bottom. So the hours on bottom are just fine. So the only thing we need to change here is the milligrams. So I'm going to put milligrams on bottom so they cancel out. And our equivalency, as usual, equates milligrams to milliliters. We have 500 milligrams in 40 milliliters of solution. So those milligrams, as we said, canceled out. Now if we multiply this through, 2,000 times 40 milliliters is 80,000 milliliters. On bottom, we have 4 hours times 500 is 2,000 hours. That divides out, giving us 80,000 divided by 2,000 is 40 milliliters per hour. Well, let's say we wanted to have our flow rate given in a different problem. Let's say in this one, we want to know our flow rate in milliliters per minute. So we have a doctor that orders 10,000 milligrams of this medication over 8 hours by IV or intravenously. They might put PIV, per intravenous. Our label, well, let's say this label is saying that we have 25 milliliters in, or sorry, 25 milligrams, I should say, in 10 milliliters of solution. So once again, we start with the doctor's orders. Now, a couple of problems ago, we had the time in there, but we didn't include it because it was not over 8 hours. It was every 8 hours or every 6 hours. And that was a medication that was administered once over that period of time. Since this is by IV, that medication is spread out over the 8 hours. So the 8 hours has to be part of our flow rate. Anytime it's a flow rate, we have to include the time. So we're starting out with our orders of 10,000 milligrams over 8 hours. Now looking at this, we have milligrams in our numerator. We look at our solution, we want milliliters in the numerator, so the milligrams have to change. We have hours in our denominator. If we look at our solution, we want minutes in the denominator. So the hours have to change as well. So it doesn't matter which one we change first. I'm going to go ahead and change the hours. Now I'm putting them on top because they're on bottom to start with. So they'll cross cancel out here. 1 hour is 60 minutes. So now the hours have canceled out, they're gone. We do have minutes on bottom now, which is what we want. Now let's get rid of that milligrams. The milligrams are on top, so we're going to put them on bottom so that they cancel out. And this is the label's telling us it's 25 milligrams in 10 milliliters. So those milligrams have canceled out. And now we'll just go ahead and multiply this out. 10,000 times 1 times 10 milliliters is 100,000 milliliters over 8 times 60 minutes times 25. Well, 8 times 25 is 200 times 60 is, I believe that's 12,000 minutes. Let me double check that. Try that again. It is 12,000. So now to get our milliliters per minute, we simply have to divide this out. 100,000 divided by 12,000, which is going to give us 8.33333 milliliters per minute. Now that's a relatively high number, 8.3 milliliters per minute. If we were doing this as a drop factor, that would give us a decent number of drops per minute. But we do occasionally run into problems that are a little bit too small a numbers. Let's say our doctor orders 3,000 milligrams over 6 hours by IV, and our label is telling us that this is 50 milligrams in 2 milliliters of solution. And we want to find this in milliliters per hour. So our orders, 3,000 milligrams over 6 hours. Milligrams need to become milliliters as we look at our solution. Hours, oops, I wanted to do that in minutes. Let's put that as milliliters per minute. I messed up there. Let's want to find our answer in milliliters per minute. That'll make more sense. So we do have to change hours into minutes here as well. Let's go ahead and change the hours first. 1 hour is 60 minutes, and the hours will cross cancel out. So we have the minutes in the denominator. That's what we want. We need to get rid of those milligrams in the numerator. And we have this equivalency from the label, 50 milligrams in 2 milliliters. So the milligrams are gone, and we'll note we have milliliters in the numerator. That's what we want. And minutes in the denominator. That's what we want as well. So we'll just multiply this out. 3,000 times 1 times 2 milliliters is 6,000 milliliters. We have 6 times 60 times 50 is going to give us 18,000 minutes, I believe. Let me double check that. So it is 18,000 minutes. Now, when we divide this out, 6,000 milliliters divided by 18,000 minutes, we get 0.3333 milliliters per minute. Now, setting an IV at 1/3 of a milliliter per minute is really tough to do. So this is where our dilutions can come back in and combine with our IV flow rates. So in order to make that an easier setting, we're going to use a dilution. And we might use a rather large dilution. It doesn't hurt the patient to have extra fluids put into their system. I should be careful there. There are a couple of disorders that having extra fluids pumped into the system could be an issue. Very few. But in most cases, having extra fluids in your system is just making sure they're hydrated so it doesn't do any damage. In fact, most of the time it's good for the patient to have the extra fluids. So we can dilute a medication with our saline or sterile water and make it a more manageable amount. Here, what I might do is I might do a 1 in. Now, since that's 1/3, I'm going to cheat, and whatever I do, I'm going to make sure it's divisible by 3. So I'm going to do a 1 in 15 The only reason I chose the 15 is because it's divisible by 3, and this I know is really 1/3. So what that means is I am going to dilute this fluid 1 in 15. So that changes 2 things. And I can go about changing this dosage in one of 2 ways. Right now, this is 50 milligrams in 2 milliliters. If I adjust this 1 in 5 or 1 in 15 dilution, that 2 milliliters changes. The 2 milliliters was before the dilution. I cross multiply and divide. It's now 30 milliliters. So that is 50 milligrams in 30 milliliters. The volume of that solution that would have been contained in 2 milliliters has been increased to 30 now. And we could go ahead and use that in place of this concentration in the formula. It would now be 30 milliliters over 50 milligrams, which would change our numbers considerably. Or we could use that 1 in 15 dilution and just use it with our calculated solution of 0.3333 milliliters per minute. Or we could write it as 1/3 milliliter per minute. And we cross multiply and divide. 15 times the 0.33333 divided by 1 is going to give us 5 milliliters per minute. And 5 milliliters per minute is a much easier dose to set on our machines. So I mentioned that dilutions come into every part of this. There's a case where it comes into those IV flow rates, as we saw before break. Okay, so then the last thing I want to go over today is I want to take some more time to look at dosages based on weight. And we've mentioned several times, and I hate to keep picking at it, but it is an issue. We keep saying dosages based on weight, but what we're really using is mass. And we're using kilograms in the metric system for our calculations here. But it's okay to say weight because what we're using generally, we're taking a standard weight in pounds and converting it into mass. And as we've mentioned before, that consistency of gravity on Earth allows us to do that. But let's say we have a label that says, I'm administer 12 milligrams to 15 milligrams per kilogram every 8 hours. And we have a patient that comes in weighing 66 pounds. And we want to know how much to administer to that patient. Well, the first thing we have to do is convert our patient into kilograms. That's going to be by dividing by 2.2. Gives us that our patient is 30 kilograms in mass. So from there, the kilograms, the weight of the patient, serves as our doctor's orders. We start with that. 30 kilograms of our patient. And we are going to use our label, or equivalency on the label, to convert that into a dosage for this patient. Now there are 2 different amounts on there, so we're going to use the 15, the larger one for now. And that is 15 milligrams per kilogram, which is saying 15 milligrams of medication is equivalent to 1 kilogram of body mass. So here we're going to put kilograms on bottom. 1 kilogram is equivalent or equated to 15 milligrams of medication. Kilograms cancel out. 30 times 15 is 450 milligrams. Now the time that we need to put back on there is that every 8 hours. So every 8 hours, or up to 3 times a day, that patient can be administered a maximum of 450 milligrams. Now, we still need to go back and find the minimum. For this problem, it wouldn't be that hard. They just set it up. 30 kilograms over 1, and we'll use the 12 milligrams per kilogram. The kilograms cancel out, and it's now 30 times 12. That's 360 milligrams every 8 hours. That is the minimum amount to administer. So that gives us that range for this patient, 360 to 450 milligrams every 8 hours. Now, the other way we could have found that 360, if this were a longer process especially, would have been to use a titration. Now, titration involves just taking an established amount. In this case, the first one we calculated that maximum amount of 450 milligrams, putting it over 1, and converting it using a ratio here. And in this case, the ratio, we have the maximum, we want the minimum. So the ratio is going to be 12 milligrams over 15 milligrams. And those cancel out. So 450 times 12 milligrams over 15 is going to give us the 360 milligrams. And we do have to put the 8 hours back on. And there were a couple of different forms that titration took to us. Let's say the doctor orders to administer medication per specification. Per specifications is basically read the label and give them the amount they're supposed to get every 6 hours. Q6D would be the way they would put that. Or Q6H, sorry, every 6 hours would be the way they would put that in their abbreviations. So the doctor wants you to administer this medication every 6 hours. For a patient, that is, let's do a 44-pound patient. Our label says to give go 3.5 milligrams to 4 milligrams per kilogram every 8 hours. So again, we first have to convert our pounds to kilograms, and that's dividing by 2.2. So 40 pounds is 20 kilograms. So that's where we start our dosage calculations off of the 20 kilograms. And we'll use, again, we'll start with the max, the 4 milligrams per kilogram. The kilograms on bottom, milligrams on top, 4 milligrams per kilogram. And our kilograms will cancel out, giving us 20 times 4 will be 80 milligrams. And there's nothing on bottom, so that's just 80 milligrams over 1. But we do have to be very careful here. This is per 8 hours. The doctor's orders were every 6 hours. So we're going to use that 6 hours to titrate our 80 milligrams. At 80 milligrams, we're going to multiply it by a ratio, by a fraction. This is over 8 hours. So we'll put that on bottom. We want to convert it to 6 hours. So notice the label of hours doesn't change. So we have 80 times 6, which is 480, divided by the 8 gives us 60. That'll be milligrams every 6 hours. So we managed to titrate that dosage to a 6-hour dose from an 8-hour dose. Now we can go ahead back to that minimum of 3.5 milligrams. If our max dose is 60 milligrams in that 6-hour period, notice again, we don't use the 6 hours in our titration. That was for that max dose of 4 milligrams per kilogram. Let's do that down to the 3.5. So this is 3.5 milligrams over 4 milligrams. Note, again, we put the smaller one on top because we're going to change this into a smaller number. This was the maximum. We want to find the minimum. So now our 60 times 3.5 is, that's 210 milligrams over 4 milligrams. Technically, by the way, this is milligrams squared. That's why when we did our dimensional analysis, they used units like that. It's not really a unit, but it comes up in calculations. We're just going to cancel that out. I have 210 milligrams over 4, which divides to be 52.5 milligrams. And of course, our time period on that, since the 60 milligrams is over 6 hours, this is also over 6 hours. And of course, the next step that can be taken in that, there are several, but the next step that we're going to do is going to look like this. So let's say we have a doctor that orders, again, as labeled, to be administered let's do every 8 hours. For a patient who weighs 99 pounds. Our label is going to say, so let's do 450 to 500 micrograms per kilogram per 12 hours. Now, one thing you'll note, all of the ones I've done here, I've gone to a bottle that has a larger time period what the doctor orders. It's usually okay to break a dosage down into smaller, more frequent doses. Going the other direction, you have a few more cautions to worry about. That's why I'm always going in that direction to where what we're administering is a shorter time period than what's recommended on the bottle. Going the other way of giving a larger dose over a longer period of time, sometimes that large dose all at once can be a shock to the system and can cause damage. Also, our label here is going to say that this is concentrated or constituted at 5 milligrams in 4 milliliters. So we want to know what to administer to our patient. Well, as always, our first step, we're going to divide by 2.2 here, because this is a 45 kilogram patient. And we'll start with the 45 kilograms. So, kilograms on bottom, we're going to use the maximum again. This is 500 micrograms. We do need to convert micrograms to milligrams. So 1 milligram is 1,000 micrograms. You could have, if you wanted to, if you just know that 500 micrograms is 0.5 milligrams, you could have just done that. Let's look at what we have so far. The kilograms have been canceled out. Micrograms have been canceled out. Right now we're in milligrams. But this is, it was given as milligrams per milliliter or in milliliters. Assuming this is a liquid medication, so we have to go on to our volume of liquid to be administered. We're going to put milligrams on bottom. That's the 5 milligrams in 4 milliliters. So now we can go ahead and multiply this out. 45 times 5 times 4 is what, 90,000 milliliters on top. On bottom, we have 1 times 1,000 times 5 is 5,000 on bottom. There's no units on bottom. We divide that out, and that comes out to be 18 milliliters. That 18 milliliters is over 12 hours. The doctor wanted us to administer this every 8 hours. So that 18 milliliters is going to be multiplied. Now the 8-hour dose will be smaller. The 18 represents a 12-hour dose, so we're going to put 12 hours on bottom, 8 hours on top. For ease of calculation, I'm going to cancel out the hours right here. 18 times 8 is 144 milliliters. Over 12, that divides out to be 12 milliliters. And now I've changed it from per 12 hours to every 8 hours. So 12 milliliters every 8 hours is our maximum dose. And we can go back and do that titration again to get the minimum dose. That maximum dose was from 500 micrograms. We need to do it for 450. And that, of course, will change our dosage again. That comes out to 10.8 if we multiply that out. We're out of time here, so let's go ahead. There is no new homework from what we talked about today. This is all kind of review of stuff we have done. But you could be looking at pages 178 and 179 out of your book, 1 through 21, the odds. Pages 184, page 184, 1 through 11, the odds on the titrations. And then also page 188, 1 through 21, the odds. So again, I will not see you guys again until next week, Monday. On Monday, we'll talk a little bit more. We'll pick up all these dosages based on weight, and we'll actually talk about safe doses and how those affect, how you have to double check any sort of recommendation. So with that, I'll let you guys go. You guys have a great week. I realize we're having one class kind of in the middle of a 2-week off here, but you guys have a great Easter, and we'll see you next Monday.